Let's suppose we have a rate of change of a population is proportional to itself. So whatever the population is now determines the rate of change of the population. So we have dp dt equals k times p, and k is that proportional constant. K is actually the growth rate. If you've taken a Calculus 2 class, you would know that this solution, you can solve this by separation of variables, but the solution this is p equals some constant k, not the same as this k, e to that k now, that k from above, times t, where k is actually the initial population. So we know that's the actual solution to this differential equation. But let's say this shows me that this population is growing exponentially without any bound. But in reality, we know populations don't grow that way. So in reality, there's actually a maximum population any species can reach before it runs out of resources, and then it can't grow any further. So how do we do that? How do we write that in terms of a differential equation? We have to introduce another factor, which is called the carrying capacity. And that carrying capacity is called n. So n is this carrying capacity. And if you notice, I put this vector 1 minus p over n. What that does, it tempers the growth of the population. So as p is small, the population grows really fast because this number is close to 1. As p gets really large, this number is actually very small, and it's going to reduce the rate of growth population. If p is equal to n, then this number is 0 and there's no more growth. So this is called a logistic population growth. So we can solve this equation too, because it is possible to solve this through separation of variables, and actually you should know how to do it, but for the purpose of the video we won't do it. So if you did solve it, the solution's in the notes, and you actually have to isolate the p's and bring it down and bring the dt up, and you have to do partial fractions in order to solve this particular differential equation. So it's a good practice for you. But let's say I didn't want to solve it. I wanted to analyze what type of solutions we have for this differential equation. Well, there's two things we note. First of all, p, this rate of change of p is dependent on just p. There's no t here. So when it's dependent, when this differential equation is just dependent on the dependent variable, we call that an autonomous differential equation. Autonomous differential equation. Okay. Secondly, in this autonomous differential equation, there are values of p that make the rate of change 0. So those values of p that make the rate of change 0, namely which are p equals 0 and p equal n, we noted before that dp over dt is equal to 0 for these values of p. These values are called equilibrium solutions. Equilibrium values of p. And what does that mean? Well, it's saying that when p is equal to these values, the rate of change is 0. Nothing's happening. It's not changing. dp dt is 0 means we have a horizontal line in terms of the t axis. So if you think about this here, we think of this as p, and this is t. Here, when p is 0, we have no change, and when p is n, we have no change. So if I start off with an initial value here, we know that it's whatever the solution is, a solution curve to this particular initial value here, it's never going to go higher than n, and it's never going to go lower than 0. So, and we'll see how to evaluate this, but the solution curve is going to look something like this here, where it's going to level off as we get closer to n. And if I start off with an initial value maybe here, well, it's never going to go above n, and it's never going to go lower than 0, so this solution curve will go here. But it will never go higher than n. And if I start off with the initial value here, higher than n, well, it's actually going, and we're going to see why it's actually going towards n and not away from n, but it will go towards n but never go lower than n. And if I start with an initial value that's actually negative, which is not practical for this particular situation, we would see it would actually never go higher than t. In fact, it goes away from t. So there's a reason why these solution curves slope in this direction, and it comes from actually looking at dp dt. That's the rate, the slope, right, for different values of p. And there's another way of determining it by finding the second derivative, which tells me the slope of the slope. So, and we'll get there. But because these solution curves go towards n, we would call n a sink. In terms of all the solutions go towards n in a certain area, and then here p equals n, and then p equals 0. So this line is the actual p equals 0 line. We know that solutions, no matter where you start, go away from it. So this is called their source. And it kind of makes sense. If you start a low population, it's going to increase until it levels off close to n. If you start with a population really high, higher than the carrying capacity, the population will decrease to that value of n, which is an equilibrium. And this negative population doesn't really make sense, but it says if you start negative, you're going to go off down on to negative infinity. So anyway, so how do we plot something like this? So we can actually plot a solution. We can actually see this solution. I've kind of given you this, but we can use software to actually plot this solution. And we're going to use I'm going to two programs. First, I'm going to go online and use a program called Desmos, and then we're going to use one called MATLAB. So MATLAB is available for you for free from UNCA, and I'll give you the code how to plot this particular differential equation and see these solution curves.